Okay, so here is the derivation. Yes, and
so this is showing us how to find the right indicator.
This is it.
Okay.
Yeah. So here will give you further understanding. Okay, so at equilibrium we have that expression. So the 10 to 1, 1 to 10 will be the color ratio, the transition, right? So you can substitute it. So 1 over 10 represents after the endpoint color, 1 over 10. Then you proceed and calculate the pH expressed like this. Then, let's say that's before the endpoint. When just before the endpoint, or at the end, the beginning of the endpoint. Okay, and then here is the at the end of the endpoint. For sure, you see this color. Okay, so you 10 to 1. So the expression for pH will be like this. So that transition right before the endpoint and right at the end of the endpoint, the delta pH will be 2. Delta pH 2 unit, by taking the difference, right? Delta meaning difference. Okay, then you get 2 pH unit. So here is the conclusion for this calculation, that your indicator need to have a coverage, okay, of at least 2 pH units, so that you can catch the color, the transition before and after.
You said that at least 2?
Yeah. Ideally, need to be 2 or bigger or larger. Transition. Okay, so remember that.
I'm sorry, another question.
Yeah.
For equation 2 and 4, they appear to be the same. Am I missing something?
Well, equation 2 and 4.
The concentration of H plus over concentration of Ln negative over the H.
Well, they are the same, right? This one is 1 over 10. This one is 10 over 1.
Okay, so I'm just looking at 3 and 4. 3 and 5.
This and that.
Okay, all right.
This 2. Okay, then you're looking at the pH.
pH, okay.
Okay, then you say, okay, there's a difference between these two, right?
Okay.
So it would be a minus between the two. Okay, the difference between the two, and 2 pH units.
Where does the minus 1 and the plus 1 come from?
Delta, meaning is a difference.
No, on the one before the endpoint is pKa minus 1, the one after is pKa plus 1.
Yeah, so you use this one, subtract that one.
We just memorize that there's not a reason for it.
Well, mathematically, so the pKa cancel pKa, right? The 1 minus minus is 2, right? Minus is 1.
Okay.
Yeah, thank you for your help, Jeremy. It's log function right there. Okay, so is it okay? And from here, you take the minus log and the minus log of this whole deal, then you end up with that. Okay, that's simple math, so review that. Let's don't drag on with that. Okay, so that's what we did mathematically. So now, how do you choose a proper indicator? So these are the criteria. Number 1, you know your endpoint's pH, right? So you match your endpoint's pH with the pK value of your indicator. So this will give you the proton concentration to have the closest match, okay, at the endpoint. Number 2, the range, that is the color change range. So it needs to have a good detection limit, so that is need to cover at least 2 pH units that we just mathematically derived and proved, okay? proof 4. Then the third criterion is the type of color, right? Then you want things like your colorless to pink is ideal. You know, if you pick one between yellow and green, is so fussy. Okay, so those are criteria. Sometimes it's a trade-off. So if you turn to the back cover page in your textbook for the color, then you will the front. Sorry. Then you can see a chart right there. So it shows you all the criteria, right? pH equal to pK, so match the pH. Thank you. And then the range, you know, some are longer, some are shorter, right? The band, the little band, and also the type of color, okay? Okay, now water is your solvent. So water itself can ionize into the ions, right? H2O can ionize, but only a very tiny amount, so 10 to the minus 7 concentration. So it's really low. Okay. Now, if a weak acid, though, if a weak acid, it is weak and has a low concentration, then the water proton could contribute. But that contribution is, again, is a comparison for the magnitude. So you will need to see whether water will contribute or not. Okay, as an example here, now this is acetic acid, 10 to the minus 4 concentration. And then here, this is chemical, is sodium acetate. This is salt of that acid. Now, if you mix the two, then you realize it is going to be a buffer, right? And the two concentrations are externally added. It's not ionized from one chemical, okay? So you add two chemicals into it, then you use this buffer equation, right? So you are solving the proton concentration and the Ka. Then simply plug in like that, strictly calculate. So this is the usual way you are familiar with. Then you will have to ask yourself, is this estimate accurate? Because you know these concentrations are fairly low and getting close to water. Okay, then looking at what's happening. What had happened here is the acetic acid, right? So the acid will ionize, you know, the ionized portion will give you these two. So this is equal to that, as indicated in that. So now your Ka up here, Ka equal to proton, this free amount of proton, that is the same thing as the proton at equilibrium in a mixture. Okay, is multiply the base, whatever you dissolve is that amount, but then your base could associate with the proton generated from here. So this portion of the proton could react with the two. Okay, so that base react with that. Then whatever down here, then is going to be less quantity because here is going to react with it, and here the quantity is going to be consumed. So when this is plus, then this is minus. Okay. So now you plug in the difference here. So here you add an amount, and here you subtract an amount. Then you end up with this calculation compared with that. So notice if you consider the contribution of reaction, then your final answer is somewhat lower than your original estimate. Okay, So keep that in mind, and we will talk about this point more so a little later. Okay, so there's an early exposure for you that, when the concentrations are so low, that you need to consider reaction. So one is add, the other one will subtract.
When water becomes significant in the solution?
Yeah, the relative concentration.